Okay, so I think the step that you had all completed yesterday was bringing it up on the sharing screen. Yeah. So you had all gone through these commands, and then some of you might have logged into GitHub and start taking a look, but that's the first thing that needs to be done. But before we jump to that part, is there anyone here, either in person or on Zoom, who have not completed these steps? Please raise your hand or send us a chat message. I see a couple of chat messages. Okay, that's good morning. Yeah, good morning, everyone. Sorry, sometimes we just jump into the depths without saying hello. So we're not seeing anyone indicating that they have not had a chance to complete these steps. So we will assume that everyone has gotten to the point where they were able to run at least up to this point. And while we are waiting, if the others want to go ahead and open up GitHub, log in. So this was still about logging in. So I think we're going to jump to the next step after this. Oh, wait. So before we do this, if you guys can go to github.com, pull up the repository that you created, you should now be able to see code in there. So Harry, if you want to share and show what the expected view should be. So everyone in person, welcome back.
Yeah, this is what it should look like for everyone.
So we're going to repeat again. The process that you went through yesterday, it was long, it probably felt painful. Do not worry, that's not what you do as a coding team member for FTC. Yeah. A lot of what you did was with the intention of teaching you and making you understand how Git works. From a pure FTC perspective, after we're done with this, you're going to see a couple of slides. One is an easy option, the other is a slightly harder option. One gives you the harder option you can follow. If you really want a private repository, then you can follow that. But if you don't care and if you're okay with having a public repository, then forking is simply so easy. You don't have to go through all the problems or all the stuff you did. And then working with the code itself through Android Studio is really easy because it's all based on the user interface. You're not going to be writing command line commands to do what you need to do for FTC. So at this point, I'm going to ask if everyone has logged into their github.com account, opened up the repository that you created yesterday in camp, and do you see all those folders? So it should basically be initialized and have code in there. Okay, because that code was what you pushed from your local computer into GitHub. That's how that code got there. And we want to make sure that you have all reached that point. Okay, if someone has not, please send a chat message or raise your hand in person as well as on Zoom. So we'll give 5 or 10 seconds to see. Okay, looks like everyone has gotten to this point. So Naman, take it away.
I'll pull up the presentation.
You don't have to stop sharing.
Okay. So now's the time where we integrate what we did with Git into Android Studio, so you can actually code. So if everyone can just go ahead and open up Android Studio on your computers, it'll take like a minute to start up.
What is sharing? So,
Um, so this is what everyone should see when they open up their Android Studio. So what we'll do is we'll go to the open button and then find where you stored your FTC robot controller from yesterday. So we stored ours in downloads, but if you stored yours somewhere else, just open that. So ours opened pretty fast because we had it set up earlier, but yours will take a while to get set up. And at the bottom, you'll see like a progress bar where it says setting up Gradle. We'll go over what all those things are soon.
you see something that's
Did everyone get Android Studio in the project opened? And everyone on Zoom as well? One more thing, you might see a lot of messages on your side that says project upgrade recommended. And it says like your Android Gradle plugin is too low or has an upgrade available. You don't want to do that because that will break your FTC code. So it's always recommended just to go and just clear that.
So just to expand on that, what FIRST does is when they create the FTC package, they for a specific year or season, they have it so that it is current with respect to some of the tools available at that point. But then a whole year passes. You're not going to see them go on updating it, so frequently, which is why you stick with what's working for the season. And then when the new season is announced, by then typically they would have upgraded what files they have to work with the newer version of tools. So definitely expect that there may be updates that you can and should do once the new season is announced. But please read the release notes and do this. Do not just go and upgrade everything to the latest, because they may have upgraded to an intermediate newer version, not the latest, because maybe the latest just got released a week ago, right? So please make sure you are reading the release notes, seeing what's compatible, and upgrading Gradle, Java version, which is JVM, or Java SDK. So they all have compatible versions to which you need to upgrade, not just the latest all the time.
So by now, I think everyone's projects should have opened and synced. So what we'll do just to test out GitHub is on the file that opens immediately, it should be a readme.md file. We'll just go here and then put some stuff in underneath the notice. So we can just say this repository contains, and then underneath that, you can just write, we use this for the FTC Coding Camp. Yeah. Now you should be able to save it. And on your left, you should see a tab underneath the folder that says commit. So you can open that and you'll see that there's a change, which is the file you just made. Did everyone get that? So what we can do now is we can click the checkbox above changes, and that'll select all of our changes. And just as we did in the terminal, you can enter a commit message here.
if you go to the three dot thing.
So as Coach Tree was mentioning earlier, your commit messages should be helpful. So you can say something like updated information in README or something like that. And then now you can just hit commit and push. It may say that you have some warnings, but that's normal, so you can just do commit anyways. And then just hit push. It may ask you to log in, you can just follow that process. So doing this is the same thing as the 5 or 6 commands you ran earlier. But this is like a much easier way to do every time you're coding and want to make a new commit. Now, when you go to GitHub, you can like refresh your page and scroll down, and you should be able to see the thing that you entered, which is we use this for the FTC Coding Camp. Did anyone not get that on their GitHub page? Have some help? Anyone online? Okay, that's good. We'll go back to the presentation then. So this was one method that we used to create the repository. And basically, we just downloaded the zip file for the FTC robot controller and then pushed it to GitHub. But another way to create a repository is to use the fork method. This is something we mentioned earlier as well. So the point of a fork is it's much easier to stay up to date to the new FTC SDK versions. So if they change something with this method, it's much easier versus with our other method, you have to manually migrate all the changes that they make.
So before we jump into this, just a quick question. Did everyone get their Android Studio to build the code that you had basically made available in Android Studio for that project? So you basically downloaded code, you pushed it to GitHub, and then you opened that code in your Android Studio. And when you do that, it tries to build the code. So assuming you have all worked with Java, you know that when you have Java source code, you have to build it. And basically it's going to compile it. And then if there are errors, it's going to tell you there are errors. So if any of you ran into build errors, let us quickly get those taken care of before we jump into this. Harry, let's go back to the previous one. So we want to make sure that you all have Android Studio with successful builds of the source code. If anyone does not, please send a message or raise your hand. So in person, do all of you have a successful build? Yep. Okay, all right. So it sounds like everyone does, and we don't see anyone raising a hand online either. So now, yeah, you can. So I think we had already mentioned, right, about how this one is time consuming. So
Yeah.
Now you're getting into
Yeah.
the fork one.
Yeah. So what we can do is we can open up the fork on GitHub. Okay. Yeah, forked. So we can open up the FTC robot controller repository on GitHub and then make a fork from there. So we can demonstrate that.
So if you're a team that is okay with having your code repository being public, we strongly suggest use this forking mechanism. It makes it a lot easier, not only to begin with, even when you need to sync the changes that first might post. So let's say right now it's at 10.3, right? On kickoff day, they're going to release 11.0. And maybe in a week, they realize, oh, we have this issue. So they may release 11.0.1 or 11.1. And then that means you need those file changes because they are probably going to be important and critical for you to get in there. If you followed the approach we did yesterday, then you have to manually go in, get all the specific files that first changed and add them to your source. There may be coaches willing to do that or software members willing to do that. But if you really don't have a reason to have a private repo, fork it. You just have to click a button and then you sync up your fork by the click of a button. You get everything that's first posted for 11.1 right away. So that's a lot easier. Yes, we have a question.
Okay.
If you don't get up the just. So,
Okay.
Next, if we walk them through the steps of opening, like in Android Studio, opening the project as a Java project. So they all did file open the Java project. Okay, can someone open here because she has.
It's over here for. I'm not able to vote.
Okay. Let's go ahead and continue then. So what we can do is we can go to the fork and click the down arrow. And we'll see that we already have existing forks because we've done this before, but you can create a new fork. And now we're on pretty much the same page we saw for making a repository. So what we'll do for this is we'll name this preseason-FTC SDK-2. Notice how, in this case, as Coach Shi was mentioning, there's no option to change it from public to private. So because you're making a fork, this has to be public. And basically, when you push your code to GitHub, everyone can see your code.
I mean, if they're following the repository.
Yeah.
Yeah. So yeah, just to clarify, it's not going to push it back to first code repository. It's going to push it to your repo, your team's repo. But if someone were to search for that repo, they can find it. So it's not like your code changes are all going back to first. It's just that the repo you've created is accessible to others if they want to look for it.
So what we can do is we can click create fork. So yeah. Kevin, do you have a question?
Yeah, I cannot, it won't fork. It's just grayed out.
Oh,
It says you cannot fork
We
because
also
you own
getting
this.
it. I think you're looking at the pre-season, the old one, the one you created. You have to go to the FTC robo controller.
yeah, you do the fork on the FTC robot controller repository. Not the one that you created, but the one that first owns.
The one that first owns. Yeah. Okay, so the one that first owns. So I uploaded it to GitHub.
Yeah.
Like the other day I uploaded it. And yeah. Why is it not working? Wait a minute. Cannot fork because you own this property. This repository,
Yeah.
I'm getting.
I think
So
I,
you have to do the fork on the FTC robot controller repository, which is like owned by first, not the one that you created yesterday.
Oh. Okay.
So
Yeah.
by forking, what you're really doing is you're getting hold of the one that first has provided, and you're literally creating a fork of the source from it. In a sense, you could keep making changes to that forked version while continuing to pull in changes from the original version. That's why they call it a fork.
Okay.
If you were to clone it, what you're doing is you're just creating a copy, and then you lose that association with the original when you clone
Okay,
it.
that makes sense.
We'll give everyone a second to do that. Did everyone in person get to it, or?
Does everyone manage to create a fork and now have, or at least at this page where you can select fork? So you may want to hover over that. Yeah, just show that. So if you can all see the drop down there, that's how you can access the fork option. And then you create a new fork from that.
So we named ours preseason FTC SDK2, but you can name yours whatever you want.
branch that tracks that.
Okay, so everyone should see a page like this once they fork it, and it should mention like preseason FTC SDK-2 forked from first tech challenge / FTC robot controller. And as you can see here, it says this branch is up to date with FTC robot controller master. So as soon as they make a new update, you'll see here that it's not up to date. And you can go here and click sync fork. At that point, it'll bring the changes that they made into your repository. Did everyone see this page? Okay. Okay, we'll go ahead and open up Android Studio now. And we can get this new project. So we can close our previous project. And what you can do is you should see a button that says clone repository, or in some versions, it might say get from VCS. So if you click that, it may ask you to log in again, but if you logged in the previous time, it shouldn't. And if you go to GitHub, you'll see all the repositories that you have. So Harry has a lot, but if you're just starting on FTC, you might not have that many. So you can go and just type in preseason-FTC-SDK-2, and you should see the one that you made. Was everyone able to find this in their Android Studio?
Yeah.
For the question of, can you show it again? Could you clarify what you wanted to see again?
Where you got the clone repository from?
Wait, are we doing cloning right now? Yeah.
Yeah.
We're still forking.
What do you mean, where do we get it from? Like where we forked
It's
it from?
a window, clone repository window.
Oh. So you should see a button in your Android Studio when you open it. It says clone repository. Or it might, on some versions, it might say get from VCS.
Yeah, get from VCS should be the one.
I can show a screenshot.
Because cloning would, it's an existing
Same thing.
repo.
Yeah. On some versions, it might say get from VCS, but if the button is in the same spot as says clone repository, that works too. So if you go ahead and open that up.
Yes.
thing.
Okay. And then you should see an option that says GitHub. and then you can go to preseason FTC SDK-2 or whatever you named it.
Right, yeah. So to Naman's point, the reason you're doing the clone here is it's still on GitHub. You have not yet downloaded it locally.
Mhm.
And the act of cloning that remote repository is what will bring it down to your local machine and make it available locally for you to start working with. So this is a clone to your local from the remote GitHub repo.
And then you can just hit the clone button. And it'll clone it. We'll give it a second, but you might see something that says trust project. Since you made it, you can click the trust project button. It is a security feature just in case you're like using code that somebody else made. And now we'll also wait for the project to sync again. Okay, and our project succeeded building. So we know that our new method also works. So you can see the difference between the two methods of how easy one is versus the other. Okay, well, we can go back and show the presentation now. We did want to briefly go over the method that you would do if you would like to make your code private.
So,
Yeah.
start with this. So,
Mhm.
the forking option is what we strongly suggest for most teams if you don't really care about having it private. But like we mentioned, if you have some cutting edge code, you simply don't want, leaked out to out on the internet, and you want to really be protective of that, then this is an option. Now, this is a fairly complex way of doing things. So we would strongly suggest that a coach be involved when you guys go through these steps if you choose to do this, or have some really highly experienced member who's done this multiple times and is comfortable doing this. We are not going to go through all the steps, like we are not going to have you go through all these steps here. We will talk about each command and what it does. These are tested, so we know it works. But if you have any questions, definitely ask us. But this is a complex approach. It's kind of more complex than what we went through last evening or last afternoon, which was just to create a copy and start using it. This one, you create a copy, you're using it, but you keep changing your remote so that you change it from yours back to first repo as remote, and then you pull the changes. After pulling the changes, you again switch back to using your regular one or the private repo back again. That's why we will explain what it does, but we strongly suggest have a coach or a highly experienced member involved if you choose to do this approach for the upcoming season.
Yeah. So basically what you would do for this, you guys don't have to go through and follow these commands. You would clone the repository locally the same way that we did earlier. You would then go and remove the ors.
We haven't done this yet.
Oh, yeah, good point. Okay. Previously we downloaded the zip, but this is cloning it from remote. So when you do that, you get all the data from GitHub, including the origin. If you try to push to that, it won't let you because you can't push to first repository. So what you do is you would remove it, and after making your own private repository on GitHub, you would set that as your new origin where you want to push to. After pushing, it'll create that repository, and you can make your modifications to that without anybody else seeing it. And then after that, you can continue coding. But when you want to make updates, which will show on the next slide, we can add it as an upstream, which is basically similar to the way the fork works, except you're doing it locally. So you would add your upstream to you set your upstream to the FTC robot controller repository, the one that first owns, and you'd merge it every time there's a new commit to that. You would have to manually track to know when there's new commits to that and do this whole process. Again, as Coach mentioned, this is kind of complicated, so you would definitely need some practice doing this before you could reliably do it in the season. Does anyone have any questions on that? All right. I think the next part is Rohan's part, or oh yeah. I'll hand it back to Shri.
Thank you, Naman. So just want to cover a couple of conceptual pieces of information before we get into actual coding. Now, most of you, if you've gone through some kind of course to learn Java, you probably have covered what is going to be spoken about in this slide here. Now, when you write your Java file, right, you're creating a source file with a .java extension, and that's where you have all your commands, your Java commands. The way that Java command is then executed is, first thing that needs to happen, you run a compiler to compile that Java file. And when you compile that Java file, you're creating something called the bytecode or the class file. Now remember, this is not the same as the object and class. Ultimately, yes, it does represent a class, but we're talking about the file with the .class extension. That is generated when you compile your Java source code. And that's also called the bytecode file. And the fact is, when you compile the source that you have using the JAVAC, which is Java compile command, you have to give the source file name that you're compiling. You can give a relative path that works also. But at the end of the command being run, it's going to generate these class files, which are called the bytecode. Now, if you learned Java where you actually took a text editor and wrote your Java code in the text editor and ran your Java C command, then you'll know what we're talking about here. But if you picked up an IDE and just started with an IDE, you may not be aware that this is what's happening in the background. But it is important to know this as a person who's coding in Java. You should at least be aware of these details. And the JAVAC command, that is available only if you have something called the Java Software Development Kit or Java SDK should be installed for the JAVAC command to be available. If you only have the JRE, which is Java Runtime Environment, then you will not have the ability to run this JAVAC command. You will be able to execute already generated bytecode files, but you will not be able to compile and create a bytecode file if you only have JRE or Java Runtime Environment installed. So please remember, you need the Java SDK in order to do software development. Okay, that's some details there. And then the bytecode file, which is the .class file, can then be executed on any platform. So you may have all heard how Java is a cross-platform language, which means you can code it in any language, and then you're able to run it on any platform, any operating system. And the reason is, when it is executing the bytecode or the .class file, it is not doing that right at the operating system level. Instead, there's a layer in between the operating system and that execution, which is why you can do it on any operating system. That layer is what is called the Java Virtual Machine, or the JVM. So execution of the bytecode requires an interpreter, which is what the JVM is. it is basically interpreting your bytecode or your .class file contents into machine language. The operating system can only execute machine language. And that interpretation is what is being done by the JVM. And when you install the JVM, you're going to be installing what is specific to the operating system you're working with, which is why it does not matter which operating system you want to execute your bytecode on. As long as you have the JVM specific to that operating system installed, it knows how to interpret that bytecode into machine language, which is specific to that operating system. Okay, I know this may sound very complex if you're new to Java, but what I would suggest is, what we just covered here. After you've done some Java, go back and listen to this, or just look at that slide and maybe watch the recording snippet. It'll make more sense as you guys go through and learn more and more of Java. Okay. And there's a reason we kind of covered all that. Oh, let me go back there. There was one thing I wanted to talk about, which is, so apart from JAVAC for compiling, the execution is done using Java space test. So you don't mention the .class extension, you just have Java and then the name of the class file. Now, in this case, that Java is for execution of the bytecode. That part will be available in JRE. You don't necessarily need SDK for that execution part, just so that you're aware.
Like click on it, kind of right.
Click on the screen.
Yeah, and then you have to. Oh,
Okay, all right. Okay. Gradle is something which you should all be aware of because you're using that under the scenes with your IDE, and you need to know for multiple reasons. One, when you're adding new packages, you may need to go make edits to these Gradle files. But let's back up here. Now, the most common processes, like we just saw now, in order to use any Java source, you need to compile the code, right? That's the JAVAC command. You saw how we had one file there. How does it work when you have your whole source folder, right? You might have, I don't know, 25 classes in there. You want to compile all of them. And after compiling them, you are going to be packaging those class files because you're not going to execute each one of those class files, and they may be dependent on each other and things like that. So they need to be packaged in a proper manner. And that's, in our case, we are creating the .apk file, which is the Android package file. There's one more really popular one for Java is the Java archive. That is JAR, popularly known as jar files. That stands for Java archive. That's another popular way of packaging Java classes together and having it ready for execution. So again, to generate that packaged form is going to be another command. Just like you had Java, JAVAC, there's going to be other commands that are needed in order to put those all together in an executable manner. And then one more thing that needs to happen with Java classes potentially is publishing the artifacts to some repository or transferring the APK file to the intended location. It could be a phone. In our case, it's going to be the control hub. See how there's various actions that need to happen, right? From the point when you finish writing your code to the point when that code becomes available on the control hub, there's a lot of intermediary steps that need to happen. Now, if you are to run all these steps manually with a command for each one of them, it will be firstly time consuming and tedious, and it'll be error prone because one mistake somewhere in the middle among all those commands will mess it up. To make it a lot more easy, what has been done in the industry is they have these build tools. So if you've heard of, long back, I'm talking about multiple or even more than 10 years ago, there used to be Ant, and then came Maven, which was really popular, and Gradle is also really popular now. Okay, so if you hear words like Ant, Maven, and Gradle, these are all build tools, or they are tools for working with your source code and making it a lot easy to accomplish certain tasks, which will then enable you to get that source code in the intended location, in the intended format. See, for you, a lot of this is going to happen behind the scenes because you're going to go into Android Studio, you hit build, it builds, and then it compiles everything, creates the package, And then when you have the control hub connected, it even gives you the option to download the APK file. So 2-3 button clicks, you have gone through several commands which were required in order to go from having just Java source to having that APK file built and downloaded into your control hub. Okay. Now, Gradle is a build tool, right? So there's going to be updates, upgrades. That's why you'll see different versions. And some newer versions might break older behavior. That is why first we'll sometimes ask you to stick with a particular version of Gradle for that season. So please remember and follow those. Now, there may be times when you could get away with a later upgrade, but I would strongly suggest do not, if that's your only machine. I mean, if you're really curious and you want to try it with a different machine, that's fine. But do not, in the middle of your season, try out things which then make your computer not able to, process and do things the same way that they were able to. A lot of this, I know our team members have tried and then, regretted it and then learned lessons. So all that happens, but just be aware that if they have something in the release notes, try and stick with that. It'll be easier that way. So does anyone have questions about what we spoke about earlier, just the whole compilation and interpretation part or Gradle? Anyone in person? So if you're feeling this is a little too complex or hard to understand, like I said, just please go back, look at the slides, watch the recording again, and hopefully it makes sense as you get more and more into FTC coding. A lot of this is really not specific to FTC coding. It is just Java coding, but it is important to know as you work with FTC code. Okay. Right. So Rohan here, who's the president of the team this year, he will be taking it from here. Right, Rohan.
All right, hello, everybody. So I'll start by talking a little bit about object-oriented programming. So assuming you guys all know Java, you've probably heard this term before of object-oriented programming. And a good way to think of it, so like a real life example is, say you have like fruits is like sort of the class, and in the class of a fruit, there's different like attributes that a fruit could have, such as weight and color. And then now an example of that is, say you create an apple, which is an object. And so an apple would be like you can think of it as an instance of a fruit, and an apple will have its like specific weight and color associated with like this object. You can also sort of think of it as like if Jill, who is an object of the class person, is eating an apple, then you can think of eat as being a method that the class person has. So that's just like a little overview of object-oriented programming. Does anyone have any questions about that? How is it set up like this? Share? Is it?
Yeah.
It's not screen share.
So can you like put it in full screen? It's like really small on the TV. It's like
Oh, do we have like remote?
just like it.
This
Yeah,
one?
yeah, your remote.
I press this to work. Yes. Yeah, I've seen it takes 2 minutes.
Okay. All right, so I'm just gonna ask really quick online if anyone has like access to their robot. Or like to a robot. Just check that. All right, so that's fine if no one has access like to a robot. We're gonna be showing everything like on our end through the camera. But I'll start by just talking about how you're gonna actually deploy your code onto the robot. So first of all, like physically, you need a cable, which is a USB to USB-C. So you can plug the USB end into your computer. And then on the control hub, there's a USB-C port. And so you're basically gonna plug the USB-C end into the control hub. So we can just show that like on video really quick. Part of this actually want? What part do you want for it? Yeah, I mean, just like sharing the connection, so. Oh. Basically, this is like where you're gonna plug, where you're gonna plug it into the control hub here. Wait, how do we remove the web? Yeah. So. Into the USB port.
Let me see it online. Not online, in person. Oh, hold on. Yeah, go ahead.
Alright, yeah, so. You guys can see you're at plug actual orange cable is up there. And basically you're just gonna need to plug the other end into a computer. So here I have like a Mac, so I just have to use this adapter. Basically plug the other end here. And then now in your, basically in Android Studio. Let me turn the red light. That sort of slows. That, yeah.
Oh, I'm gonna stop now.
So one second, we're gonna share the screen of a different laptop. How do we know that? Oh, skip this clip. So yeah, so now you guys can see that over here. Over here, this like Red Robotics control hub thing popped up. So that means that our laptop is basically connected to the control hub. And so now if you actually wanted to download the code, what you have to do is just click this button here, like run through. Just like, no, I was sharing on this laptop. Yeah, so that's how you're gonna download code.
Wait, just make sure everyone got that.
Yeah, are there any questions about that process? Any questions in person? Were you guys kind of all able to see like in the camera or here, like whatever? All right, I'll show it again. Right? So basically, you plug this end into the control hub over here. And you plug this end like into the laptop. And now you can see in Android Studio, it's showing Pixel 5 here, right? And then now that changes to Rev Robotics Control Hub. So that means that we're connected.
So we can't see all this code. I think you guys built this code, correct?
Oh yeah, this is don't worry, we're gonna get to that.
Yeah, you'll get a chance to write this code. This was just a demonstration of how you connect to the control hub and download code. So just want to repeat, add at this point. This is the mechanism this is one of the two mechanisms that you can use, which in this case, you are just directly connecting a USB cable. The other possibility is to use Wi-Fi and something called an ADB bridge from Android Studio to your control hub. Now that's easier in Windows. It's slightly harder with a Mac, but we have heard of how people have done it with a Mac. We tend to do this only with Windows, but with Mac we just find it easier to use a USB cable. We won't necessarily get into that part, but you know that you can always connect into the control hub from your laptop using a USB cable.
Did everyone in person like kind of understand that process? So I'll also talk a little bit about like the structure of the FTC robot controller SDK. So if we go over to Android Studio, uh, close everything, you can see at the start, you basically have two main folders, FTC robot controller and team code. So the place where you should be writing like your custom code is in the team code folder. So basically you want to drop it down and then go in Java. And so now you can see like through this file path, this is where you're gonna write all of your custom code. So now you guys shouldn't have anything in here yet, and that's like perfectly fine. We're gonna add code in a second. Yeah, and then I also want to show you one more thing, which is the sample code. So the FTC robot controller SDK has a ton of sample code, and you can access those in the FTC robot controller folder. So you basically want to just drop down through this file path, and you can see they have like a bunch of like sample things here. So this is like a pretty good resource because it helps you sort of like understand a lot of stuff that you can do with that FTC SDK. And they also have like stuff like April tags. So if you're trying to learn how to like program April tags, this is a pretty decent resource. Yeah. Are there any questions about that? All right. So with that, I'm gonna now start talking about actual coding. So no more of GitHub. We're gonna start doing.
Excuse me.
Oh, yeah?
In the sample code.
Sorry, what was that?
Where did you find the sample code?
No,
Oh,
we,
yeah.
yeah, we got the external dot sample. Yes.
Yeah, the sample code is here. And basically, you want to drop down FTC robot controller and then the Java folder, and it's basically in this path. And then it's in external dot samples. Oh, it is. Wait, how do I add this? Simply just call one. Okay. Also, wait, should I share on this? But does this have like image you have set it? No, can you program on this? No, then use yours. Go get this code and open it. Or something like stop sharing. Copy video from them. Good video. Yeah, so that the FTC SDK offers two off mode classes. So they offer something called linear off mode and just off mode. So in this camp, we'll be using linear off mode because it's a little bit simpler and easier to understand. But the main difference between the two is just how they're structured. So I'm not going to really dive into into normal off mode, but we'll talk about the structure of linear off mode. So there's basically two main stages. There's the initialization stage. This is where you're going to run all the code that's necessary to basically set up your robot before you actually press play and run the program. So this includes stuff like your motor configs and your webcam setup. And then the start stage is where you actually run your auto or teleop programs. This is where you're actually going to put the code for like moving your motors or checking your gamepad buttons. Yeah. And also this link here, you guys will have access to this PowerPoint slide, but this link here is a pretty good like article about the differences between linear off mode and the normal off mode if you're interested in that. Are there any questions about this? I'll also sort of show it a little bit more in depth, like when we actually start coding. Yeah. All right, so we're gonna be writing our first program now. So I'll start by going back to Android Studio. So basically the first step is create a new file. We're gonna want to create a new Java file. So you guys won't have any of this code here, but you're basically gonna want to navigate to this folder. And if you right click and select new and click on Java class, and you can name this like something like we can call it test motor. And it's gonna give you the option to add the file to Git. So unless you're like creating this file as like sort of something personal that you don't want to be pushed to the rest of the repository, you should always add it. Oh, so to answer your question, yeah, it's kind of, they both have their advantages. It just depends on like which structure you like more. So I suggest reading that article that was linked in the slideshow. That'll sort of help you make the decision about which one to use. But they both have like pretty similar capabilities. All right, so the first step whenever we create any new program is we're gonna need to extend linear off mode. So right. Yeah. And now it's gonna give us an error, and the reason for this is because you need to basically add a method run off mode. So there we go. Also, is everyone able to see it? I zoomed in a little bit more too. Uh,
Make this non-link.
oh yeah, it's like that.
Just drag it over. I don't know. Yeah. So,
So basically, we'll start by creating a new object, which is we're gonna basically be creating a DC motor object. Oh, oh wait, guys, all right, we might need to go in a breakout room with Sandra. Yeah. Yeah, so Sanjay, we'll put you in a great breakout room with someone that can help you sort of get up to speed. So wait, Harry, I'm gonna put you in the
Breakout room, make point.
oh. Who's that in the room with Sandra? Wait, Aurav, I'm gonna put you in the breakout room with Sandra. Just yeah, just help him like get up to speed with what we can do. Alright. Yeah, so yeah, you guys should do. Oh yeah, Kevin, did you have a question?
So mine's underlined, but it's already imported the linear mode.
Oh, it's
Oh, I have to add that bit.
this
That's
run
why.
off mode. Yeah, yeah, you need this run off mode.
I'm used to just going a plain up mode, so it's a little different.
Oh, yeah, yeah. So Sanjay, you should be able to wait, the breakout is yet. Like, how do you do that, I guess?
This is it. You've already opened one and can you assign Harry to this?
Uh, yeah, so Sanjay, you should be able to
Maybe.
join breakout room.
Okay, this will come out. Yeah, this sometimes.
We're all the same, meet everyone.
I think that was
Oh,
the intent.
well, you can leave, I think there's. We're ready to continue on. Yeah, so we're gonna start by creating a DC motor object. So the place you're gonna create like all your objects is up here, right before the run off mode method. So we can literally just start by typing that. And one pretty important thing in Java is something called camel case. And it's basically just like the common practice of how to name your variables. And so the way you do this is you start by the first word is lowercase. And after that, each word starts with a capital letter. So we're just going to call this test motor. And so now the next step is we need to basically initialize this like with the hardware map. And so the hardware map is basically the way that so each motor will be plugged into the control hub, right? Into some specific port. So the hardware map is how your code basically recognizes which motor is what. So in this case, like through the code, we're basically naming this test motor is we're basically giving it a name of like this here, the T capital T EST motor. And so now in our driver hub, when we create our configuration, we're going to want to basically put these exact letters into the port which our motor is plugged into. So we'll be demoing that in a second. So we're gonna do this now. So, test motor equals. So here we can put. And so this is basically assigning the new object we created to an actual motor that's on our robot. And then now, so I talked earlier about the two stages of linear off mode, which are initialize and the start stage. So the way we differentiate those two is through this, through this wait for start block here. So anything above wait for start is part of your initialization stage, and everything below wait for start is part of your actual starting stage. So on the driver hub, when you run a program, you're basically gonna have a button that says init on it. So when you press init, it's gonna run the initialization stage of your program. And then when you press the actual play button, it's gonna run the rest of your program, the start stage. So this we can just put this telemetry update to basically know that everything in our initialization stage is finished. Otherwise, especially when you're getting into things like setting up your webcam, they can take like 5 to 6 seconds to finish running all that initialization code. And if you start the program early before the initialization is finished, it's not going to work. So it's always important to have this telemetry update to, so that you know that your robot is initialized before you run the rest of the program. So we're going to add that. And always remember to add your telemetry.update, otherwise it won't actually show up on the driver hub. So basically, we finished our initialization stage now, which was this code. And now the way you run these motors is pretty simple. We can basically, this DC motor class has basically a bunch of methods. And so it has a set power method. And the way this works is you can give it a value, a double value between -1 and +1. And that's basically gonna control your speed. So -1 means it's spinning at max speed in the negative direction, and +1 means it's spinning at max speed in the positive direction. So we can just put something like 0.5. And now I'm just gonna make it spin for 2 seconds and then turn back off. So to do that, we can just use really simple sleep block. And then we can set our power to 0. So are there any questions about any of this code, in person and online? Also, just give everyone a little bit to finish writing this code. Is anyone in person struggling with anything here or having any questions?
And those of you who have done this before, maybe not necessarily with Android Studio, or maybe you have dabbled with Android Studio. If you have questions based on some roadblocks you might have hit when you were trying, please do ask those questions. So don't feel like you're supposed to just stay with exactly what you're seeing here. As we go through this now, if you suddenly have a question about hardware maps, feel free to go ahead and ask those questions.
Is anyone not finished with copying down this code? Like, am I good to move on, or is anyone still working on it? All right, Anya is still working. All right, that's done. Oh yeah, just let us know when you're done and ready to do that. So can we get the driver hub set up in the robot window? Oh, you know what? There's one quick thing we have to add. So if I go back here, you guys can see there's this @teleop symbol here. So basically over here you can put @teleop or @autonomous. And what that's gonna do is in your driver hub, you have when you're selecting a program, you have 2 sections to select it from. You have the teleop section and the autonomous section. So we're just gonna be using like teleop for this demonstration. But it's important to remember to always add this. Otherwise, when you actually deploy your code and check your driver hub, if you don't have an teleop or autonomous, it's your program's just not even going to show up. So we should add that in. Yeah. Oh, yeah, sure. Let's see. All right, is everybody ready to move on to the next step? So I'll basically be demoing it here in person with our test robot. And I'll also be showing you guys like how to configure this motor on the driver hub. So the hardware map part will kind of make a bit more sense. Uh, yeah, I'm not seeing everything. So, oh yeah, we'll get started then. So, wait, no, you like this? Yeah, always. Yeah. All right, so as you guys remember earlier, the first thing we need to do is actually, and stop sharing side. Like full screen. All right, so the video should be full screen for everyone now. But if you guys remember earlier, the first step was basically plugging in the cable to the control hub and the laptop. And then I'm just going to deploy the code like how we did it here. Yeah, now you guys might have seen the control hub light change to a blinking blue. So that means that the code is deploying and the control hub is basically restarting. All right, and it'll take about like 20 seconds for this process to finish. So now you can see on our driver hub, we're reconnected to the hubs. So on the driver hub, if I click these three dots up here and click on configure robot, which is the third option, it's going to take us to this screen. And so now I'm going to create a new configuration over here. So now you can see we have control hub portal, so you just click on that. And now the motor that we're going to be running is this one here, and it's connected to expansion hub port 0. So that's where I'm going to configure it. So I'm going to click on expansion hub here on in the driver hub. And then now I'm going to click on the motors option here. And so now in port 0, I'm going to select the Builder 5202/3/4 series because that's the motor we're using. And now you can see I have the option to enter the motor name here. So if you guys remember in our code earlier, we had named it test motor with a capital T and capital M. So I'm going to copy that exact name. And if this is case sensitive, and if you have like even one letter different, then they're not gonna map to each other. So you can see we have test motor entered there. Yeah. Now I can just save this configuration. And I'll call this save. Right, so now you can see we have our new coding camp configuration here. So you can just activate that. Now we'll go back. And now a good way to, if you have multiple configurations, a good way to check like which one is your active configuration is you can sort of see it over here. So it might be hard to read, but that says coding camp. So we know that that's the active configuration. All right, so now to select our program, this right drop down is where our teleoff programs are going to be. And so our program was called test motor, which is this one here. So now you can see we have the init button. So I'm going to press that. Now you can see it's finished initializing. Now if we run it, this motor should. And after 2 seconds. Oh, is everyone able to see that like in person and online? Yeah. All right. I'll run it again. All right, so that's basically really basic. First program, making a motor move for 2 seconds. Does anyone have any questions about like the process I did like with the driver hub and running the programs? If there's no questions, I guess we can move on.
So I must confess, I'm a little surprised that we're not getting any questions.
Yeah.
Please don't hold back. Please don't be like no one else is asking questions. That's good. We have a hand raised here. Go ahead.
Oh, sleep method, it basically just means like the entire, so your code is running on something called a thread. And it means that that entire thread is basically just gonna stop running anything for 2 seconds and then resume. So we put in 2000 because it's in milliseconds, but if you've ever done Scratch, you can sort of think of it as like a wait block. It's the same thing pretty much. Very much again.
And also, if anyone wants something to be repeated, please let us know. We'll be happy to do that. Because the intention at, for the past few minutes and going forward from here is so that you are equipped to write your first FTC programs. And that's why we have a motor where you can just, make the motor move. And then we're going to do the same with the servo, try to use a distance sensor, kind of get some of those basics out of the way. When you all learned Java, I'm sure the first Java program you all wrote was Hello World, right? Or something to that effect. So these are really your Hello World programs for FTC. You're learning how to do some basic things. And then before we end, we will make sure that you also have a drive base coded so you know how to get a drivetrain moving along. Okay, we have 2 hands up. That's good. You
Okay, so it would be elementary that has 9 below.
That is absolutely right. Yes.
Yeah, also you do the coding conference for like another time.
Sure, yeah. Well, you want the whole thing just from beginning?
Yeah.
Just once again. Okay, sure.
Well, I'll just like run through the entire file. Okay. So, I mean, first of all, you have your package and imports. Yeah.
So package and import, from having worked with Java programs, I'm hoping you all have an idea. Package is simply the folder structure or directory structure where your source files exist. It's starting from a certain root. And there are things like class path and so on. I don't want to confuse you with too many of those details. Hopefully you know what is class path from Java, but if you don't, I would suggest go look that up. So package is kind of related to that, and so is import. Import is when you're importing certain class files and they are located in a structure, a package structure, which was already defined. Now, if it is something from your code, then you would have it in that directory structure. If it is something from a third-party package or a third-party library, then you would have included a jar file. And some of that is happening behind the scenes in your dependencies. So again, don't want to confuse you too much with that, but the classes that you need for this source to execute, you are including those.
Yeah, like for the imports, for example, like you can see like when we created our DC motor object, it just automatically imported this like the class for DC motor. So and this at teleop, so that symbol was basically on your driver hub. You had the autonomous and teleop drop downs. So putting at teleop specifies that you want this program to be listed in the teleop sections. And now there's like class name, and we extended linear off mode. And this is our creating our DC motor object. And this run off mode, this is like, it's sort of similar to like the main method in a normal Java program. It's basically what's going to end up running when you actually run the program. And so the first step in here was for our initialization stage. We wanted to map our DC motor like on the hardware map. And that kind of, I hope you guys like kind of understood how this correlated to what we did on the driver hub. And then we assigned some telemetries that we know when the initialization stage is finished. And then the wait for start, that's just separating the initialization stage and the start stage. And this was our motor running code. Did that like walk through make sense? Yeah. Wait, do you have any other questions?
No, I don't think we had any stuff.
All right, so in that case, we can move on to our servos. So servos are pretty similar to motors. First of all, does anyone not know what a servo is? I think we talked about it earlier in like the hardware thing.
No, we
right?
didn't.
Oh, we hadn't. All right.
You
Oh, yeah, so-
share.
Yeah, if you guys just look at like the video, we'll show you guys what a servo looks like. Yeah, so it's basically this thing right here. It's sort of similar to a motor, except it's basically it doesn't have like a full, it can't just continuously rotate like through the code. You basically can set a position rather than setting a speed. So it has like between -1 and +1, you give it a position, that's gonna snap to that position. So it's pretty useful if you have some sort of like claw type movement. It's good for controlling both type of things.
That said, there is a mode called continuous rotation mode. There are a few times when you might want to use something like that, but it's primarily used when you want precise movement to precise locations, and it cannot really manage a whole lot of load. You cannot have heavy loads being lifted with a servo. You'll end up just breaking them. But their biggest selling point is the fact that they're capable of going to 1 degree precision of movement. And so there are many applications like in claws as well as certain arms where you want it to be in specific spots, you can use those.
All right. Yeah, so we can just what we'll do is create a new program. So basically in our team code folder, can do the same thing as last time, add a new Java class. And then this one we can just call it like coding camp. And make sure to add that to Git. So basically in this file, I'll be like I'll be using this to demonstrate like all the things I'm going to show. I'm not going to create a new file every time. The first step was extending linear operator.
So everyone in person, have you all been able to write some of this code? Or are you just following along? What are you choosing to do? We can make this source available to you if you want. So in a day or two, we are going to be providing the recording, providing the slides. And if you'd like, we can provide the source that was here.
Yeah.
Okay.
But actually, we're just going to copy paste all our code from test motor and put it into this new class. That's because we're going to need the motor for a later demonstration with the distance sensor. So when you paste it, just make sure you change the name back to okay. Yeah. All right, so the creation of a servo object is really similar to the DC motor. You can just create. Yeah, so it's just giving me an error because I need to import the class. Yeah, so we just import class, yeah. And the hardware map initialization is really similar, or it's the exact same. And this one we'll just call it test server. Yeah. So now you guys should have basically this line of code added and this line of code added. And now I'm just gonna comment this out real quick. And so the way you control the servo is basically through the set position method here. And so in set position, you can give it an input of anywhere from negative or anywhere from 0 to 1. So 0 would be basically one end of its range of motion, and 1 is the opposite end. So I'm going to start by setting it to 0 and wait 2 seconds. And then I'm going to set it to 1. And I'm gonna wait another 2 seconds and just set it back to 0. So basically, this should make it move like all the way from one end of the spectrum to the other end, and then move it back. I'll just keep this up for a little bit so that everyone has time to copy it down.
And we'll actually use this time to take our quick 15-minute break. Let's make it a 13-minute break if you don't mind today. So at 11:40 Pacific, we will resume. Till then, that source is out there open. So please make sure that you use this time to copy. And if you need it scrolled, actually, can you take off that bottom part so more code is seen?
Oh, yeah.
I mean, the message part. Yeah, so please go ahead, make sure that you have this one completely copied and compiling fine. And if you have any questions as you're going through this, now is a great time to talk about the questions. Let's see, what else? But yeah, please do get your snack and take your break. So everybody in person, now's the time to get your snack.
Also, if anyone has any questions about anything we've covered today, now is like the time to ask them. Because we have like a little bit to talk about it.
What? Oh, it's actually cool. Yes, on the slide, it is always not. Stacy, the non student comes to the first set. Okay, I'm going to yeah. So everyone, we do have some important things we want to cover. So in the interest of time, what we'll do is this one here was just moving a motor, right? There's no encoder or anything like that. It was just free rotating a motor. The next one will be moving a motor along with using an encoder. The encoder is the part which tells you how many rotations have happened and things like that for the motor. So what we'll request is we're going to, I think everyone hopefully has had enough time to copy this. We're going to put that one up, and then we're going to just talk through that rather than type it out. So if you want, you can make a copy of this and modify it to reflect the new code, which will be put up here right now. So go ahead and put up the one with encode.
Yeah, and also we'll this like repository, this source code, we'll send it out to you guys. So if you guys don't copy something down, don't worry, you guys will have access to it. So this code that's pulled up now is like the next program we're gonna be doing, which is basically moving the motor using the encoder. So you're gonna notice we have this method here, move motor to pose. So that's like the key difference. I'll go more into it though after our break. Yeah, Kevin, you had a question?
I noticed these meetings were being recorded. Are we gonna get a copy of the video after?
Yes, you guys.
Okay, we are going to resume in roughly 1.5 minutes.
Okay, hello, everybody. Our break is over now. So I'll start by just demoing the servo code we had created earlier. So, I'm going to stop sharing so that you guys can all see my screen or the video. I'm going to start by just demoing the code.
If anyone who's remote actually has a control hub on there or a robot on there that they're trying to use and run this code on, please let us know so that we are aware that you have a robot that you're trying this on. And maybe we can help out.
Let me go ahead and edit our coding camp configuration. And let's go to the expansion hub servos. Because the servo we're going to be using is connected to expansion hub 40. So you select from here. The last selection is servo. And it's called S servo capital S. So I'm going to save the configuration. I'm going to go ahead and turn on servo. Yeah, so you can basically move everything here. All right.
So something valuable to share about the servos. As you can see, there's a dead zone here, right? This region here. So you saw that it moved around this way till here, and then back here this way till here. Now this, so let's say out of 360 degrees, there's about 50 or 60 degrees of dead zone where the servo will not go. Now I know there are some newer servos like the 5-turn servo from Gobilda, and there may be others which are capable of rotating beyond 360, even in the servo mode. Almost all of them are capable of simply rotating around in the continuous servo mode. So that's not what we're talking about. When you have it running in the servo mode, they usually have a dead zone. So when you're mounting your hardware or mounting your servo, you need to make sure that your robot does not actually need the servo to be operating in that dead zone region. This is kind of hard to understand, but think of it this way. There's no way in software where you can change exactly where the deadband is. It's physically constrained. So right now on this servo, this region is the physical deadband. So let us say I actually need the servo to rotate this way. Then what you would have to do is physically make sure that your whatever hardware you're mounting is changed. The angle is changed so that it operates only in the required region. If it's hard to explain beyond this, but if any of you have further questions, please do ask us. But when you are working with the build team, when they're putting the server together, please make sure that they understand this, that a servo simply cannot be mounted however you want. You have to take into consideration where the deadband is when you're mounting a servo, because you cannot override that with software. It's a hardware limitation. It's a physical limitation. Okay.
So hopefully you guys were all able to copy down that moving the motor with the encoder. Yeah, so this code, hopefully you guys were all able to copy down this code during our break. So I'll just run through it so that you guys can understand everything that does. First of all, we have our packaging and ports. Basic structure. So we're creating that S motor object that we did in our first program, and we're just setting up our hardware map and whatnot. But the main difference is this method down here. So hopefully you guys all sort of understand what a method is. Like assuming you have prior knowledge of Java. So it's basically called move motor to post, and we have a parameter, like an int parameter. So we're giving in an encoder pose. So what this means is this is basically the encoder position we want it to move until. So the way it works is we start by setting the motor power to 0.5, and then we open a while loop, and we're basically checking that our current position is less than the encoder position. So this means that once it does get to equal or greater than our target encoder position, it's going to basically exit the while loop and set the power to 0. So hope you guys all understood that. Does anyone have any questions about this method? Anyone in person have questions about this?
So everyone in person, you've copied down the other file, right? The one with the encoder position. Okay. Anyway, this source will be made available, but for now, you can. We hope you understood what was explained, and you can go ahead and watch the execution in a moment.
Yes, basically the way we use this method is we call it here, and I pass in 10,000. So the way encoders work is they're basically measured in something called ticks. So 10,000 ticks is going to be like a few rotations, sorry, three to 5 rotations. And you can search online to find, like, based on which motor you're using, you can find how many ticks is equal to 1 rotation of the motor. So yeah, it's always been efficient.
Exactly, and so as mentioned, the RPM of the motor is going to be what determines how many ticks per rotation hold good for that specific motor. Because you can have motors ranging from 30 RPM, which is 30 revolutions per minute, which means the fastest it can turn is 1 whole turn in just 2 seconds. And then there are some as fast as 6,000 RPM, which means they turn 10 times in a second. So all that is achieved using gear mechanisms within the motor. But that also means the encoder values are simply not going to be the same across all motors. So if you swap out 2 motors, with, I mean, forward motor with a different motor of different RPM, the code will have to also be updated to match the change in the ticks per rotation. What that means is if you need the motor to turn 10 times and you change the motor to a different speed, you will have to go change the encoder values. Please remember that.
So wait, one quick thing to add is, so this telemetry here, we're gonna basically see on the driver hub, when we run this program, we can see the, current condition updating until it gets 10,000. So I'm just gonna go ahead and demo it. We don't need to change any of our configurations since we have already set up the test mode. So basically I selected our program, Coding Camp motor here. I'll initialize. And now you guys can just watch this motor. So basically it's gonna keep spinning. And yeah, there we go, it stops. Oh. Yeah, so
We're just restarting the robot. Yeah, check rotations, yeah. That's more than distance.
yeah, now we're gonna move on to the distance sensor. All right, let me share this.
So given that we're going to be sharing the source code, I think at this point, time is best utilized just walking through the code quickly and seeing it execute. And then you can put that code together, because I don't think anyone raised their hand or indicated that they are trying this out on a robot. So in the interest of getting through more topics, we would just talk through the code, execute it, and then when you have the source code available in the next day or two, you can execute it on your local robot if you have one.
All right, so hopefully you guys can all see this. So I'll first explain what a distance sensor is. I think we talked about distance sensors earlier. All right, so distance sensor, it's basically what it sounds like. It basically projects like an infrared light, and it when it bounces off of something, it can tell how far away it is. And there's different units you can get this measurement in. We get it in centimeters and inches. So the distance sensor that we have is a Rev 2-meter distance sensor. And I can show it. Yeah, so it's basically this thing right here with the little green light. If you guys can see it. Alright, so I'll talk about how to program this. So the class we're going to be using, we'll create this object is just distance sensor class here. We can create a test distance sensor object. And also, I'm just gonna, yeah, don't worry about this touch sensor thing. And so the way you set this up in hardware map is slightly different. So you can see for our motor and servo, we were able to do like hardware map .motor.get. The distance sensor doesn't have this option, so you just have to do hardware map.get, and then you basically feed in 2 parameters in the .get, do distance sensor.class and the device name. And then so it's just our utilization one. And so what this program is doing is we have a while loop here. And so you can see we have while off mode is active. So what this means is basically while our program is running, so the way it would exit this while loop is only if you press stop on the driver hub. So it's basically gonna keep going through this while loop as long as we have track. And in here, we're adding the distance that our distance sensor is currently detecting. So you can do that by using the .get distance method. And we're just specifying a centimeters unit by using changes to inches. One. And so in here, we just have a conditional that's saying if our current detected distance is less than 10, then we're gonna set our motor power to 0.5. Otherwise, we're gonna set 0. So what this means is if we like, so I put my hand in front of the distance sensor and it's less than 10 centimeters away, our motor should move. Otherwise, our motor should be off. And also, we Nick Tom had this. So I'll give everyone a little bit of time to just copy this down. And then we'll then virtually.
I think we decided we'll talk through and go on. Just because we really want to get to know the layer.
So actually need to move on because we are sending all the source code out. So I'm just gonna start by deploying our code. Now I'm gonna stop sharing sound and switch to our camera.
As you're watching, just to make sure there's no confusion, this one here is the color sensor. That's not what we're using. This is the distance sensor, and that's the one we're using for this specific purpose.
So the way we're gonna configure the distance sensor in the hardware map is. Oh, okay, so the distance sensor is plugged into something called an I2C port, which is this one down here. So it's different than digital or analog.
Both the color sensor and the distance sensor and by have robotics, those are called I2C sensors.
So we can see in our background.
Okay.
Now, the driver hub. This is the place, we plug this into the I2C bus. So you don't want to scroll down the I2C bus. And so now it's called the red meter distance sensor. And in the code, we just called it the test distance sensor. So has that with it. If I run the program, you can see in order to run these. Yeah, you can see the current distance. Yeah, it's at 819. Now if I put my hand here, you can see it's getting smaller. And now if I bring my hand, I'm close to it. So we're gonna back up close. Good. Let me show the node.
Oh,
Yeah, so this is the node up here. Now I'm gonna bring my hand closer and now you can see it's right in front of the distance sensor, so I can see like 5. The already rotates and I think it will. Oh, okay. The distance sensor can be pretty useful if you're trying to say like drop some game element into like a specified location, you can use it to basically drive to a certain distance to like put there. Alright, so with that, I think we'll move on to the database drivers, right? How active. And we talk for yeah. Alright, so let me share my screen. Alright, so this is the program that we have for our drive base. So this stuff is all the same, but now we have a few more motors. We have right front motor, left front motor, right rear, and left rear. So these just refer to the different wheels on the robot. So let me show the button. So for us, yeah, so this here is the front of the robot, and then this is the back of the robot. So this is left front, this is right front, this is left rear, and this is right rear. Now back in the code, we're just doing our hardware map setup here. And then now these two lines of code here, because on the robot, right, the left side motors and the right side motors, they're pointing in opposite directions. So that means that if you spin all of them at say like a power of 1, even though that power is positive, the robot's not gonna, all the wheels are not gonna move in the same direction. The wheels on the right are gonna move in opposite direction. So that's why we're just reversing them, because we want setting a power of 1 to mean that the motors are moving forward. So that's the reason for this reversal. And so this is the actual sort of drive base code. So we have another while offload is active. And so we're gonna notice like a new thing here, which is new gamepad. So the way you program a gamepad is pretty simple. You can literally call like the gamepad1 object. And so by the way, if you didn't know, on your driver hub, you can have two sort of gamepad users. So gamepad1 will refer to user 1 on the driver hub, and gamepad2 refers to users. And so now the gamepad1 object has basically different state for every button. So basically all of these methods will return a union. And the joysticks, however, they will return a double value or a float value. So that's what we're using here to drive the robot around. So the first of all, this type of driving is called robot centric, which basically means that all of our movement is relative to the robot, not the field. So it's going to be like it's the more traditional way of driving the robot. So we want the left stick Y, which is, you guys look at the camera. Yeah, this is our left stick Y, basically moving this up and down. And this is the left stick X, and then this is right stick X. So we want our left stick Y to be for moving forward and backwards, and we want our left stick X to be for strafing, and we want our right stick X to be for turn. So that's essentially what we're doing here. We basically have our left stick Y value, right? And the way we're going to turn is basically if we want to turn right. So if we move our right stick to the right, we want to add power to the left wheels and subtract power from the right wheels. So that's what this is doing. And I know that might seem counterintuitive because it's adding for right and subtracting for left. But the reason for this is just because of how the positive and negatives work on our joystick. But what it's gonna do is, we move the stick right, it's gonna add power to the left wheels and subtract power from the right wheels. And if we move the stick left, it's gonna add power to the right wheels and subtract power from the left. Wheels. And then now for strafing, it's a little bit different because when you're strafing, the diagonal wheels are moving in the same direction. So that's why for our right front motor, it's adding the left stick X. And for our left rear motor, it's also adding the left stick X. Whereas for our left front motor, it's subtracting. And for our right rear motor, it's subtracting. So basically this culmination is gonna allow us to have like pretty good movement with our scan. Guys. So we're gonna go ahead and demo this. So. I'm not gonna show you guys the driver hub configuration, we've already talked about that a lot, and this is not a new device, this is just a motor. Suction. Wait, show it. Connect the controller. As first of all, the way you connect the controller to your driver hub is you basically plug it into one of these USB ports here. USB 2. Yeah, USB. And then if you see up here, you can see the user 1 and
Wait, it's
you can see the user 1 and user 2 options up here. So the way you would switch those is basically on the gamepad, if I click start and B, it switches it to user 2. And if I click start and A, it switches it back to user 1. So it'll show that switch. So yeah, you can see how I'm able to switch between them. You can change the robot. So now you can see, get a little bit forward and backwards. Does anyone have any questions about everything we've covered so far? I know we went like really quick throughout all of like the distance sensor and this stuff. Yeah, I'll show the code again, but we will be moving on now, and this code will all be sent out, you guys. So don't worry if you like miss copying it down.
so just a quick point here. The reason we hurried through some of this is in the past we used to cover machine learning and because FTC used to support TensorFlow and machine learning, and you had things you could do where you use that API. But that's been replaced of late. And Pinpoint is one thing which has become really popular. And Limelight 3A is another one. So we want to at least briefly touch on those topics so you don't go in without any context when you start your season. That's why in the interest of that, we wanted to hurry through these because you'll have access to the code, you'll have access to the recording. So please go through the recording if you want to kind of remind yourself what we spoke through once you have access to the code. And so at this point, we're going to have Sashmit, who's our director of software, who's actually in college and high school age. He's going to start talking about localization and some of the other advanced topics that you would benefit from knowing. You guys help? Yeah. Rohan, can you open up the version 2.2?
Which computer do you want to?
Discord.
Sure. We're gonna end up. I'm not sure. Do you need like the Android Studio here? If you don't need Android Studio, don't get a point. Oh. Oh yeah, then okay. But you don't need to deploy. Don't need to deploy. Wait, this has Android Studio. I love stop signs.
Okay, just keep it here.
Yeah. So it should,
Okay, do we have the updated version of the?
no,
I got sure. What was coding?
So we finish up to the slide before this. Coding up material papers.
Yeah.
Okay, all right, yeah, we can take it from.
And then we just.
So.
Is this considered the one that has audio on this? All right. Okay. Okay, so now that we've talked about how to use the skills of moving motors and using the sensors, now we wanted to get into some of the more a complex aspects of FTC coding. And one of those things is localization. So this is incredibly important, especially in autonomous, because when your robot has to move without the aid of a driver, it needs some way of knowing where it is on the field, or else your errors from each movement are going to compound, resulting in your robot being unable to reliably execute a certain sequence of movements every time, or repeatedly, right? Every time the errors in your movements are going to compound differently, meaning that it's going to end up in a different position with the exact same code. So localization allows you to correct errors in your robot's movements during autonomous so that you have precise and repeatable motions. Now, it's also usable outside of autonomous if you want to code driver automations in Teleos. Localization is also pretty important. And some common driver automations that use global positioning would be like an auto aim system or auto align, or any automation that would move your robot. So just a bit more into what exactly localization is. So as you see here, it's the process of your robot using sensor inputs to determine its position and orientation on the field. So position is the X and Y coordinates, and orientation is the heading angle of your robot. And so we call this a combination of position and orientation. We call it a pose. So when you hear the term robot pose, it means X, Y, and heading. Now, a global position is your robot's pose relative to a fixed coordinate system for the entire field that does not change depending on your robot's starting position or depending on the alliance that it is on. So the reason we call it global is because every robot, every thing on the field is on the exact same coordinate plane, and that coordinate plane never changes. It's relative to the field, which doesn't change. All right. Any questions here? Fine. No? All right. So there are two main methods that we use for localization, which is odometry and vision. So we're going to be going through odometry mainly here, and we're going to be coding an example of how to use that for localization, but there's also vision with APO tags that are going to be on the field. Okay, so odometry. Odometry is a method of localization that uses sensors to track the robot's movement relative to its starting position. So it's very important that whenever you initialize an odometry computer, like the pinpoint, which you see on the screen, that you
let it know what your robot's starting position is. Otherwise, it's going to assume it's 0, 0, which is the corner of the field. So that it's your robot's not starting at the 0, 0. But odometry uses these dead wheels. So you see here, with those two wheels, those are called dead wheels because they're not powered. There are encoder wires that go between these dead wheels and the odometry computer. And those are the sensors that track how much each of the wheels are rotating. And that is how we measure distance. Now, the pinpoint computer also has an IMU. An IMU is like a gyro sensor that would measure the direction of movement. So we have the two dead wheels that measure distance, and then we have the IMU or the gyro that measures the angle. So if we know the distance that the robot has moved, as well as the angle at which it is moving, we can construct the line along which it has moved, which will tell us the current position of the robot. So you can think of this like walking in the dark and counting the number and direction of your steps to know where you are. And the point of that analogy is to show you that odometry is blind. Odometry has no visual reference. All it knows is how your robot is moving along the ground. All it has is those two dead wheels and that IMU, that gyro sensor. Now, you don't need a pinpoint odometry computer to do odometry. All you really need is the dead wheels and the IMU. Your controller already has an IMU, and so really all you need are the dead wheels. However, the pinpoint computer is a specialized coprocessor that makes this easy by doing all of the math for you. It will take in the measurements from the IMU and from the two dead wheels, and it will do all the calculations required to compute your robot's position. And all it does is it gives you the position. It's a few simple functions that you can use to retrieve the position. So not only does that mean less work for you, but also less work for your control hub, because all the math is not going to be executing on your control hub. It's going to be executing on the coprocessor of the computer. Yes.
So where's the zero? And
It can return in whatever. It's not going to return in encoder units, like I'm talking about a ticks.
Yeah.
Yeah, it's not going to return in ticks, but you're right that the computer itself will actually get the encoded data from the dead wheels in ticks. So if you didn't have the pinpoint computer and you were coding your own odometry system just using the dead wheels and your control hub's IMU, you would actually be getting the encoder data in ticks. But as I said, the computer does all the math to make this easy for you. So it will actually report your robot's global position in distance units, and you can configure that to whatever you want. It can be centimeters, millimeters, inches, or feet. And the heading angle, that third component of the pose, could be either in radians or in degrees. Okay. Any other questions? All right. So, as for how these pods work, as you see on the camera, oh, no, I'm just making the pointer visible. Okay, so as you see here on the odometry computer, there are 3 ports for encoder wires. One says X, one says Y, and one says I2C. That might be a bit hard to see. So each odometry unit comes with 2 odometry pods, one for the X-axis and one for the Y-axis. The X-axis is forward and backward movement, and the Y-axis is side to side. So we call the X-axis forward and the Y-axis straight. And then this I2C port that you see here is the one that connects to your control hub. So all sensors that connect to the control hub are either analog, digital, or I2C. And you'll see that your control hub and your expansion hub have all of these 3 types of ports. So the pinpoint odometry computer is an I2C. Well, it operates with the I2C port. So the way you are going to connect this to your control hub is with this third I2C port here. All right. Okay, so now we're going to talk about how to use this in software. So it's pretty easy, but we need to configure it first. There are some things that it needs to know before it can track your robot's position. The first thing is the offsets. The pinpoint computer needs to know what point on your robot is considered its tracking point. The tracking point of a robot is the point whose global position is considered the global position of the robot. So when we say the robot's position is this, what we really mean is that the position of a certain point on the robot is this. Now, that tracking point is usually the center of the robot. And the reason is because when the robot turns, the point's X, Y position will not change. If you choose to, if you choose to have it be a different point that's not the center of your robot, then when your robot makes an in-place turn, the X, Y coordinates of that position will change. So that's why it's usually the center. Now, as I said, the pinpoint computer needs to know exactly where this tracking point is relative to the positions of the X and Y odometry pod. So as you see here in this image, you can see the two odometry pods here, the Y odometry pod, or the strafe pod, and the X pod, or the forward pod. We always measure offset distances perpendicular to the pod's direction of motion. So for example, this X odometry pod here is going to measure forward, it's going to measure forward and backward distance. The dead wheel that it has is going to rotate forwards and backward. So the X pod offset is going to be measured perpendicular to that direction of motion. So as you see here, this is our tracking point, the center of the robot. So the X pod offset is the distance from the center of this dead wheel to the tracking point, which is 84 millimeters. Now the Y pod offset, the Y pod rotates side to side. So the Y pod offset is going to be measured forward and backward, perpendicular to the direction of motion. So as you see here, that distance, the Y pod offset, I keep doing this, the Y pod offset is 168 millimeters. So we're going to go through how to configure this in code, but you need to make these measurements whenever you are mounting odometry pods on your robot so that you know what the offsets are between the pods and the tracking point. This is probably the most important of the configurations. It also needs to know the type of odometry pod. So there are two types of odometry pods, swing arm and 4-bar. The reason we have these is so that you don't need to have an exact mounting location of the pod. So odometry pods need to be mounted at a certain height above the ground. If they're too high, the pod will not touch the ground, and there's no, the dead wheel is not going to be measuring anything if it's not touching the ground. And if it's too low, there's going to be too much pressure on the ground, which will restrict how freely the dead wheel can move. Does that make sense? So that would mean that there is an exact height above the ground that your dead wheel needs to be mounted, or else it's not going to give you an accurate measurement. Obviously, this is not feasible. So we have types of odometry pods that rotate. The 4-bar pod goes up and down, and the swing arm pod rotates like this. And this ensures that it will touch the ground even if the pod is mounted a little bit lower than what it should be. So how do I show this? Okay. Is there a way I can hold it on side? Okay. Okay. Can you just hold this in place so I can show? Oh, yeah. Okay. So I'm just going to try to use my arms here to demonstrate how a swing arm pod works. So a swing arm pods rotate like this. They have a spring which will force them into the down position unless they are pushed up by the ground. So if the ground is here, the swing arm pod will swing out as far as it can before it hits the ground. mounted the pod a little bit higher. It will swing out lower so that it can still touch the ground. And if you've mounted the pod a little bit lower to the ground, the pod will swing out less. But no matter what, the wheel will still be touching the ground so that you don't need to mount the pod at an exact height to ensure that it touches the ground and is not overly pressured into the ground. And these two pods have different encoder resolutions. So we'll see in the code that depending on what a type of pod you have, you're going to need to configure a different encoder resolution. Resolution is how many ticks per unit of motion the encoder will give you. All right. Now we also need to configure the direction of the pods, depending on how you mount the pod. You can mount it like this, or you can mount it 180 degrees around like this. Depending on how you mount it, the direction of motion will be different. So sometimes a pod will need to be reversed, and the computer needs to know that. And then the final configuration, which we need to do, is the starting position. As I said earlier, odometry will measure the position of your robot relative to where it started, because it doesn't know where your robot is starting on the field. So you need to tell it the global position of your robot at the point at which it starts. All right. Are there any questions here with the software configurations? Okay, this is a bit complicated. So if you have any questions that come up if you are actually doing this, feel free to refer to the pinpoint documentation. And we can actually paste that in the chat. Okay. No. No. Okay. All right. I just pasted the link to the pinpoint documentation in the chat. So if you have any more technical questions about that, or any questions that come up as you're trying to use this on your own robot, that's a great document to refer to. All right, so if no one has questions with this, we're going to move on to the actual code. So there you go. So this is a very simple demonstration code intended to configure and read data from the pinpoint system. It does not control the DC motors, the drive motors. So how this is going to work is you're just going to push the robot around and it's going to read out the position that it has measured. And beyond the configuration, there are a few methods that we need to talk about. The first one is pinpoint.update. Very similar to a telemetry.update. This is the method that updates the position of the pinpoint. If you do not call this method, then your position is never going to change. So it's important that you call this in a loop. So as you see here, there's a while op mode is active. So this is a loop that's going to run until the driver presses stop. So it's important that we call the pinpoint.update function in this loop that will run continuously as long as the op mode is active to ensure that we're always updating our pinpoint's position no matter what. Now, when we get the position of the pinpoint, it's going to be a pose2D object. Pose2D is a class that is provided by FRC. It's an inbuilt class. And the position, as I said earlier, has X coordinate, Y coordinate, and a heading angle. So the object that will take all these position measurements into one variable is going to be a pose2D object. So we're going to get the position as opposed to the object, and then we'll be able to use methods to get the X, the Y, and the heading from that pose2D. All right. Any questions before we jump into the code? No? Okay. All right.
So we do know these are some really complex topics, especially if you've not dealt with this before. But please use this opportunity to kind of get a rough idea, get some context, and you have the resources that are being made available, and you'll have the slides as well as the recording. So hopefully when you get to a point where you are using these mechanisms and these hardware and then need that kind of code, you're able to come back, reference this, and utilize them.
All right. So if we're good to go, let's start coding. Do we want to walk through the actual code? No. Okay. Okay. So this is the code here. This would be something that you could just copy and paste into your Android Studio and run on your robot. So let's look through it. Okay. There we go. All right. This is just the package imports here. You'll notice that there are some extra imports here that you need, such as pose2D. You'll need that. You'll also need this go build a pinpoint driver. Oh my God. Okay. So just ensure that you have those imports in addition to the ones you normally have. I think if you're on Android Studio, it should maybe automatically put these in there. All right. And this is a teleop file. This extra thing here, name equals FTC Camp pinpoint no driving. That's just an input you can provide to this teleop configuration here that will change the name of the op mode, the name as in how it will appear on the driver hub, to something that's not the name of the program. Okay. This is the variable to hold the pinpoint sensor object. So very similar to how we had a DC motor variable or a servo variable at the top of our previous programs. You're going to need this go build a pinpoint driver variable here at the top to store your actual pinpoint object. That's here. And everything else is going to be in your run op mode of functions. So all the configurations are obviously going to be initialization code. So they're going to be before this wait for start line here. So before we do any of the actual software configurations, the first thing we have to do is retrieve our pinpoint sensor from the hardware map or from the configuration. So very similar to how we did this with the DC motor and with the servo. We're going to do hardware map.get, and the name that we have for this in the configuration is called pinpoint. Okay.
So you can click it to push.
Oh, may not see. Oh, right. Okay.
Oh yeah, like just like.
Okay. Okay. If you couldn't see earlier, you can see now. I hope. Is there anyone who's having
Maybe.
trouble doing this?
Maybe zoom in.
Zoom in. Okay.
Like just go kind of like.
Okay. If I zoom in more, it's going to cut out some of the code.
That's
Okay. Is there anyone who has a trouble seeing this? You okay? If you want to move closer to the front, you can. Or here. Is this better? Okay. All right. So as I was saying, the first thing that we have to do is retrieve it from the hardware map. Whoa. Okay. We have to retrieve it from the hardware map. So we're going to go through how to configure this later, but in the configuration, we have named this pinpoint sensor pinpoint, all lowercase, one word. Okay. So now that we have the actual sensor object in our code, it's time to configure it. First thing we have to do is set the offsets. So we have measured the offsets to the tracking point on our robot, and on our robot, the tracking point is the center of the robot. So we have measured offsets of 66 millimeters and 42 millimeters. If you don't want to do it in millimeters, you're free to change this distance unit. You're free to change this distance unit here, but we measured it in millimeters. Once you've set the offsets, it's time to set the encoder resolution, which is essentially the type of odometry pod, because each type of odometry pod has a different encoder resolution, and then as well as your encoder directions. So the encoder resolution that we have is the one for a swing arm pod, because we have the swing arm pods. And then the encoder directions, the best way to set this is with trial and error. So start off with both the X and the Y pods being forward, and then just try moving the robot around and seeing if they're correct. The positive X direction is forward, and the positive Y direction is the left of the robot. So when you move the robot forward, the X coordinate of the position should increase. And when you move the robot to the left, the Y coordinate should increase. And if either of those is backward, then you should change your encoder direction for that axis to reversed. Yes.
So what unit of measurement is the offset in?
Offset, so you can see here, it says distance unit dot mm, right? The third input into that set offsets method is distance unit dot mm. Distance unit is a class that you're going to have to import. But yeah, if you wanted to be inch, you just do distance unit dot inch. But yeah, and if you wanted to see more into what these classes are, you can just search up FTC distance unit Java docs, and you'll be able to see documentation for this class. But yeah, these are in millimeters of offsets. Okay. So as you can see here, we've set the encoder resolution to the swing arm pod, and our X pod is in a forward orientation, and our Y pod is in this reversed orientation. Okay. Now this function here, pinpoint dot reset, pause, and IMU. And this is very important. It resets the position to 0, 0, 0, and recalibrates the IMU. Recalibrating the IMU is a very important step that you should do before beginning a match. So before you start autonomous, you should always recalibrate your IMU. Now there's two IMUs you have to recalibrate. There's the one on your control hub, which is completely different. This is the one on the pinpoint computer. As I said, the pinpoint computer is its own coprocessor, independent from the control hub. So it does not use the control hub IMU. It has its own IMU that needs to be recalibrated in addition to the one on the control hub. So this is the function that we use to do that. Pinpoint dot reset, pause, and IMU. And after this, we need to set the robot's starting position. And all global positions are always going to be pose2D objects. So the pose2D constructor, well, takes, I don't know why it's not, okay. It takes 5 inputs. The 3 numbers it takes are the X coordinate, the Y coordinate, and the heading, but it also takes units for those positions. So you see here, the first input is distance unit dot inch. So that tells us that the X and the Y coordinates are going to be in inches. The 2 inputs that follow that, the second and the third input, which here are both 0, but they should not be 0 in your code, are going to be the X and the Y coordinates. So this tells us that the X coordinate is 0 inches and the Y coordinate is 0 inches of the starting position of the robot. And then these last 2 inputs here are for the heading angle. So the angle unit tells us the unit at which the unit in which the heading angle is going to be, and that last input there is the angle itself. So when you start autonomous, your robot is going to have a global position, and this is how you're going to tell the pinpoint computer what that position is. And that's all. That's all the configurations that this needs. So after you've done this, the pinpoint computer has all it needs to know to actually begin tracking your robot's position. So at this point, we can do a wait for start. All right. And here, remember, all the code after this wait for start is run code. So it's only going to execute after the driver presses play on the driver hub. And this here is a run loop. So it's a loop that's going to execute. It's going to repeatedly execute while the off mode is active. So it's important that we put pinpoint.update here, because we want the pinpoint to be updating the position continuously whenever the off mode is active. And now how do we get the positions? So there's this function called getPosition, and we want to assign this to a pose2D object. And now to actually get the X, Y, and the heading components of this position, we're going to use these methods, get X, get Y, and get heading. Now these methods will all accept an argument of the unit. So we want to get the X coordinate here in inches, the Y coordinate also in inches, and the heading in degrees. Now the reason we're using inches instead of metric units is because Andy Mark, who is the supplier of all the field elements, as well as the actual game manual, all use inches. So inches is the more convenient unit to use in FTC. All right. So this function here will just get the X coordinate of this pose 2D in inches, and very similar logic for the Y and for the heading. And what this program is going to do is just put those coordinates into a telemetry. And then of course we have this telemetry to update at the end here. So as you can see, this code does not operate any of the drive motors. All it does is configure the pinpoint system, read the position that it's giving, and put that on the telemetry. Meaning that we are going to be pushing this robot around to get the position to change. All right. So does this code make sense to everyone? Are there any questions? And we're going to make this available to you. So if you want to, if you have the pinpoint computer and you want to try this out with your own robots, you can do so at home.
It can you go down like to the bottom.
Yes. Yeah. Any other questions about the code?
So I'm going to request, especially if there are members here who are experienced and have maybe dealt with pinpoint to some extent. I'm sure you had questions or reached situations where you felt like you could use some help from someone who's done this before. If you were in that boat, please use this opportunity right now. If you have questions from recent years, or actually this past year that you've tried this, now is a good time to talk about that.
All right. So with
When
this,
I'm trying to set the encoder resolution, it's saying that it's showing an error for
it's showing an error on this line, the
Yeah,
set
this
encoder
line.
resolution. Okay. The most likely cause is that you haven't imported this go build a this class here. So this go build a pinpoint driver dot go build a odometry pods. That is part of an inbuilt class that go builder has provided. So if you haven't imported the go builder pinpoint driver class, then it's going to give you an error. Do you have this import in your code?
Yeah.
Okay. Can you read the error, or actually, do you want to share your screen so I can see the error that it's giving?
I'm coding on a different laptop, so
Okay.
I can.
Yeah, if you can just read it
Yeah,
out.
if you can just read the error then.
Okay. So I've said pinpoint dot set encoder resolution go build a pinpoint driver dot go build a odometry pods dot go build a swing arm pod pinpoint, and then I've said pinpoint dot set encoder resolution go build a pinpoint driver dot encoder direction forward comma go build a pinpoint driver.
Okay, so is that the error?
No, so you read
Yeah.
out the line of code, right? When you're seeing an error, is it in the compilation? Is it at the bottom? Could you?
It's saying create variable create local variable for go build a pinpoint driver.
Okay. So are you sure you have the import up
Please.
there?
Um,
Otherwise, it's possible that you haven't capitalized this properly.
Great. Please check capitalization, and also, if you're doing this in Android Studio, the SDK should have this already, right?
I click so. Yes. Yeah. Also, please ensure that you have the latest version of the SDK and you have all the.
Great. So is this the SDK that we as part of this
Yeah,
stamp we
yeah, yeah,
downloaded?
yeah.
Okay. Okay, so is the import statement at the top that you have for Google, the pinpoint driver, giving you any error?
No, nothing.
No. Okay, so that means that you have it in there. So I would check a capitalization and syntax across this line, because if it's asking you to create the Go build a pinpoint driver locally in your program, that means it's not recognizing that it's something you've imported. So I would check capitalization of this Go build a pinpoint driver and ensure that it's the same as your import statement. If
Okay.
that doesn't work, it could be because the Go build a pinpoint driver itself is missing in your SDK. It's possible that your import just isn't giving you a syntax error, but will give you a runtime error if you actually try to execute the code. So if that is the case, you may have to download this Go build a pinpoint driver class from online.
So,
Okay.
so last year that used to be the case. You needed to download a couple of files specifically from Google Dev. And I think they provided it as their own SDK, which was laid on top of first SDK. But from what we're seeing now, version 10.3, it does by default already include the Go build a pinpoint driver class. So that file is already included. We just confirmed that.
Okay. Let me see.
Okay, yeah, so I'm not sure then exactly what's happening. If you do have the latest version of the SDK, which is the 10.3, and you capitalize both your import statement and this Go build a pinpoint driver here on the line that is giving you the error, then it should work. I would actually try executing the code to see if it actually does give you a runtime error. But if it does, yeah, I'm not exactly sure what's happening.
Okay. Thank
Okay.
you.
Yeah. Okay, so are there no more questions on the code or on pinpoint in general before we get to the actual execution of this code on our example robot? All right, okay. So before we execute this code, we obviously need to configure our pinpoint. So very similar to how we configured the DC motor or the servo, we need to configure the pinpoint, right? So
Yes.
okay. So here on our, yeah, I'm gonna stop sharing so that you guys can see. Yes, and it's a spotlight. Okay, cool. All right, so here is the driver hub again, and we're gonna go back into the configuration. Okay, we're gonna use this coding camp. So the pinpoint computer that we have on our robot is plugged into I2C bus 1 on the control hub. So we're gonna go to the control hub. And these are the I2C buses. So we're gonna go to I2C bus 1 and click add. And we're gonna scroll down. And you see here, go build a pinpoint odometry computer. It's running off the screen, but this is what we want. So the go build a pinpoint odometry computer. And if you remember from our code, this pinpoint, all lowercase, one word, is the name we assigned to the sensor when we got it from the hardware map. So we're going to use that same name here, and then just click done and save the configuration. All right. Okay. So now we're going to try running the code. Okay, so you can see here, the telemetry is giving us the current position of the pinpoint. If you remember, we initialized the pinpoint's position to 0, 0, 0. So x coordinate 0, y coordinate 0, and heading angle also 0. So this is exactly what the the telemetry is showing right now. You can see there's a bit of an inaccuracy in the heading angle, and that's just a small amount of gyro drift. It can happen when you don't initialize your robot when it's completely still, but with this little of an error, it's okay to continue for now. But please make sure that both for the sake of the IMU on the pinpoint and the IMU on your control hub, that you always turn on your robot when it's in a stable state. Okay, so with that, you have to put this on the table. But let me show the telemetry here. Yeah, so just observe the telemetry here as I push the robot around. So actually we should show the robot as I push it. Okay, so I'm gonna be pushing the robot. Oh, but this is forward. Okay. So this is the forward direction. This is the backward direction. So if you remember, the positive x-axis is forward. So I'm gonna push this robot forward just a few inches. And
Focus is on the
okay,
robot. Okay, yeah, now it's.
okay. And you can see the x coordinate became negative 6.6386. So it recorded movement in the proper axis, but it looks like we reversed our x odometry part.
Can you pull it back the other way?
And now if we pull it back, we should see the opposite happening to the x coordinate. Yeah, you see? Now the x coordinate is positive 12 point.
Then can you turn it around? Just rotate it around.
Yes. Well, let's do y first. Okay, so the y-axis is side to side. It looks like it thinks this is the front of the robot, which means the positive y-axis should be the robot's left, which is this way. So if we move it to the left,
Yep.
the y-coordinate became positive, and it should be opposite if we move it the other way. All right. Okay. Does that make sense? So it's using the exact same axis and just recording the position. Now we're going to turn the robot. So counterclockwise is always going to be positive for any IMU, both the IMU on the control hub and the one in the pinpoint computer. So if we rotate this robot counterclockwise, the angle should be positive. I'm going to try to turn it as in place as possible, but there might be some
That's working.
X and Y change. And there we go. We see heading angle close to positive 90s. You'll notice the X and Y did change slightly because my turning isn't perfect. But yeah, and we can turn it back to 0. Perfect. Yeah. All right. Okay. Are there any questions there? Any questions on how we did that? Yeah. All right. So in that case, we have time. Okay. So we are going to go back to the slides. Sure. And we are going to briefly talk about other methods of localization. So, there. All right. So just one last thing on pinpoint, that this program obviously was just pinpoint. We had nothing else in this program except pinpoint. You can obviously put this in any program that you have. These same initialization steps need to be there. So whatever this program has before the line wait for start, all of these 6 initialization lines, you just can copy and paste those lines into the initialization code of any program you want. And then it's just the same pinpoint.update, pinpoint.get position, and then these functions here to get the X, Y, and heading coordinates of the position. So you can put this in any program you want, so that you can use it with the actual driving code of your robot. Okay. So with that, let's talk about the other method of localization, which is vision. So when we have a camera on a robot, and we can use a webcam or a Limelight 3A. This robot here has a Limelight 3A. Okay, has a Limelight 3A. I'm going to turn it around so that in-person attendees can see it.
Yep.
And then, so this camera over here that says Limelight, that is, I don't know. That is a Limelight 3A. Yeah. Look like this. Pretty small camera. This is not an ideal location.
Okay, you can take this.
Okay. 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 It looks like this. There we go. It's this small thing. And it has a camera as well as a coprocessor that you can use not only for April tags, but also for other things. And we'll talk about that later. Sure. Okay. So if you want to use a camera for localization, you're going to need April tags. Now, since the 2023-2024 FTC season, there have been April tags around the field. Most of them are on the field wall in place of those old navigation images that they used to have. But we also saw April tags being mounted directly on field elements. The April tags are fiducial markers. A fiducial marker is a fixed reference point that is used to determine the location of other objects. So April tags are very much fixed. They're placed at known points on the field. And by looking at one, we can determine exactly where our robot is on the x-axis, the y-axis, and the rotational axis relative to the April tag. So the April tag library can analyze any given camera frame and can detect an April tag, and then can use that detection to figure out exactly what the robot's global position is. Library itself finds the robot's position or the camera's position relative to the tag. But by knowing the global position of the tag, we can use those relative distances to find the global position of our robot. And that is exactly what the coprocessor inside the Limelight 3A can do. Yes.
Also, would you like pair like the webcam with like a distance sensor to figure out like where you are, or you just use or just use
You just use the April tag. Yeah. So the cool thing about the April tag library is it can figure out exactly where your robot is relative to an April tag just from seeing it. So that's why April tags are really powerful. Yeah.
So just to add a couple of things here. See, you have a square image that you're looking at, right? Now, depending on the distance, that image is going to be smaller or larger. That aspect is actually taken into consideration to determine the distance. And also, when you look at a two-dimensional object, a square from an angle, it's going to be skewed. It won't look like a perfect square, right? The lines will start looking diagonal. And that aspect is also utilized to figure out, with respect to the April tag, what angle you're looking at it from. And so that is why you do not need extra hardware. Just the fact that the visual look of the April tag from wherever you are to the camera, all those geometrical aspects are taken into consideration and processed to give you your position.
Yeah, and that's a really important thing because if the vision is the only thing that is telling you where you are relative to an April tag, that means that the farther away you get from the tag, the less reliable your position is going to be. Also, the more angled your robot is relative to the tag, the less reliable your position is going to be. So there are all these things that need to be taken into consideration when you evaluate the trustworthiness of the pose you get from an April tag detection. There are usually two main parameters of a detection that you're going to use to figure out how accurate it is. One of them is called average tag area. So how much area the tag occupies on your camera frame. The more area it occupies, it means two things: that you are looking at the tag more head on and not at an angle, and also that you're closer to the tag. And the second parameter is tag count, the number of tags that you see. The more tags that you see, the more sources of positional information your camera has to determine the position. So obviously, the more tags you have, the more accurate your position is going to be. All right. Now, the reason that vision-based localization is so powerful is that it can be used to recalibrate your robot's position. So odometry, the advantage of using odometry is that your robot always has it. You're not dependent on whether your camera can see a tag or not. No matter where your robot is or where it's facing, you always have odometry to determine your position. But odometry is a bit inaccurate. The IMU that it has can drift. The dead wheels can slip, and so it can accumulate error over time. And so we can use vision-based localization to recalibrate the pinpoint's position, but we can only do that when we have a reliable detection. So it's important that it's best if we use both vision-based and odometry-based localization together, because we have odometry that can be used whenever, and then we have vision that can be used to recalibrate this and correct errors in the odometry so that we don't get accumulation of that error. Okay, so do we want to go Limelight UI?
It's 1 o'clock, so.
Yeah, okay. So there is documentation online for the Limelight 3A that it has a whole online UI. You just need to run a USB wire from your computer to the Limelight device, and then you can access that Limelight UI. That will not only show you what the camera is seeing, but if it is detecting any April tags, will visually indicate that detection, as well as tell you the global position of the camera that the Limelight coprocessor has calculated. So we're not going to show that right now for sake of time, but there is a lot of great documentation available on the Limelight 3A that you can use to get started, not only on the hardware itself, but also on the software. Okay.
So I know some of you who are here in person, this is your second year of FTC, and you guys have dealt with Limelight in the past. So Limelight as well as Pinpoint. Do you guys feel like you got to know what you might have been wanting to understand? Do you think some of those gaps were filled with these topics?
Yeah.
So for those who are dealing with this for the very first time, I know it quickly went from tedious yesterday to a lot of information today. And the reason for that is the intention is, we got you started and then took you to a point where you will have new information that you will have to learn through your season. And you may feel like, wait, I don't even know where to start. This is to give you that starting point. Obviously, you're not going away with all the information you need to build your autonomous completely, right? But you have some knowledge of the building blocks that you need. Pinpoint, April tags, Limelight 3, and then you also have some context about it. So it will need you to read, learn a bunch of stuff, and come up with the code. But we're hoping this gave you the building blocks that you would need to achieve that.
Yeah, and we're going to be posting this PowerPoint, of course, as well as the Pinpoint code, so that if you are implementing this and have any questions or need to reference this PowerPoint again, you can. We're also going to be sharing documentation links. So Limelight 3A documentation is available online with just a quick Google search. And then we have already sent the link to Pinpoint documentation online. Okay, there's a question in the chat. Will you have to modify code to use April tags in different lighting? So the code that actually detects April tags is part of the April tag library. So you can't actually go in and change that code. But there are definitely lighting limitations that you have to consider when you are using April tags. If it is too dark or too bright, sometimes the April tag will not be detected, but the range of lighting conditions that this April tag library can tolerate are relatively pretty wide. So I don't think you should be super concerned about lighting. But yeah, you definitely cannot modify any code that's in the April tag library. So any code relating to detection itself is sort of in that black box library. Does that answer your question? So it's quite amazing what this library can do. And the Limelight 3A coupled with that library can pretty much just give you a position just by looking at something. And using this in combination with odometry will give you a continuously available and a pretty accurate global position that you can use, number one, for autonomous, but also for any automation that you want to do. All right, so with that, we had a slide here on computer vision, but we're not going to go through it. If you want to look through this, you can. This one's a bit more out there than localization. It requires more work and a thorough technical understanding. So if this is something you're interested in, like OpenCV or other CV libraries that we have, you can definitely read documentation on this, help you get started. And yeah, this I think is the end. So we would like to open it up for questions one last time. Is there any questions you have on anything we've covered? All right. No questions? Okay.
So everyone, thank you so much for being here for this camp. We really hope that you got to learn a lot of information and it helps you make for a better season. And all the best. Good luck for your season, everyone. And we are here. So you all have our team email, which is frc9023@gmail.com. If you have questions, please feel free to contact us. We will say that once January comes in, our season starts. It probably will get really hard at that point. But before that, you can expect responses, in a timely manner. And following this, in a couple of days, we will be posting the videos. You will be getting the presentation sent to you and the code sent to you to the registered email addresses. If there's any questions, let us know. And any feedback anyone wants to give us now, feel free to go ahead. We will be around for at least another 5 minutes. But if you're done and nothing else to tell us, then all the best for your season. Thank you. Did we take the manual down? Yeah.